Download this code from codegive.com, link in the description below. OK, let's dive deep into ipsec's authentication header, protocol. This tutorial will cover the AUS functionality, its structure, how it works, its security implications, and a simplified code example, to illustrate packet manipulation, not a full-fledged implementation. Module 5 Lecture 2, IP Security, IPsec, Authentication Header, Protocol. Introduction. IPsec, Internet Protocol Security, is a suite of protocols used to secure IP communication. It provides security at the network layer, Layer 3, of the OSI model, allowing you to protect data as it travels across the Internet or within a private network. IPsec is widely used for VPNs, virtual private networks, secure remote access, and secure network-to-network connections. Within IPsec, there are two main security protocols. Authentication header, focuses primarily on data integrity and authentication of the origin of the packet. It prevents IP spoofing and ensures that the packet has not been tampered with in transit. Encapsulating security payload, ESP provides both confidentiality, encryption, and authentication, integrity, and anti-replay protection. This tutorial focuses specifically on the authentication header, 1. The purpose of the authentication header, The protocol's primary goal is to guarantee the following. Data integrity ensures that the packet's content has not been altered during transit. Authentication verifies the identity of the sender, preventing IP spoofing. This ensures that the packet genuinely originated from the claimed source. Anti-replay protection, optional can optionally include a sequence number to prevent attackers from capturing and retransmitting valid packets. Important note: does not provide confidentiality, encryption. The payload of the IP packet is transmitted in clear text. If confidentiality is required, ESP must be used. 2. A header format. The header is inserted between the IP header and the transport layer header, example TCP, UDP. Its structure is as follows. Let's break down each field. Next header, 8 bits identifies the type of header that follows the header. This could be TCP, 6, UDP, 17, ICMP, 1, another IPsec header, example ESP, or any other IP protocol. Payload length, 8 bits specifies the length of the header, in 4-byte, 32-bit, words, -2. This means it's essentially the number of 32-bit words after the payload length field itself. So if the payload length is x, the total length of a header in bytes is x plus 2, *4. The minimum value for payload length is 3, meaning a header of 20 bytes without authentication data, but its value depend on the length of authentication data. Reserved, 16 bits. These bits are reserved for future use and must be set to 0. Security parameters index, SPI, 32 bits. An arbitrary value that, together with the destination IP address, uniquely identifies the security association, SA, for this IPsec connection. The SA contains the security parameters, algorithms, keys, etc., used for the processing. The receiver uses the SPI to look up the corresponding SA in its security association database, SAD. Sequence number, 32 bits. A monotonically increasing counter that is used for anti-replay protection. The sender increments the sequence number for each packet sent within the SA. The receiver checks the sequence number to ensure that the packet is not a replayed packet. The receiver keeps track of the highest sequence number received within the SA. Packets with sequence numbers lower than a certain threshold, replay window, are considered replays and discarded. This field can be optional if the SA is configured without anti-replay protection. Authentication data, variable length contains the integrity check value, ICV, calculated using a cryptographic hash function, example HMAC SHA-256, HMAC MD5, HMAC SHA-1, based on a shared secret key. The key is negotiated during the Internet Key Exchange, IC, process. The ICV covers the entire IP packet, except for certain mutable fields in the IP header, example TTL, header checksum. The length of the authentication data depends on the specific cryptographic algorithm used. 3. How A works. Here's a step-by-step explanation of how A works. 1. Security Association Establishment * before A can be used, a security association, SA, must be established between the sender and receiver using a key exchange protocol like IC, Internet Key Exchange. The SA specifies the cryptographic algorithms, keys, SPI, and other security parameters that will be used for A processing. 2. Sender processing *. The sender determines if outbound traffic requires ipsec A protection based on the Security Policy Database, SPD. The SPD specifies which traffic flows should be protected by ipsec and what security protocols to use, A, ESP, or both. The sender calculates the integrity check value, ICV, using a cryptographic hash function, example HMAC SHA-256, over the entire IP packet, including the IP header, A header, and the payload, except for specific fields in the IP header that are allowed to change during transit, example TTL. The calculation uses a shared secret key that was negotiated during the IC process. The sender constructs the A header. Sets the next header field to indicate the protocol type that follows the A header, example TCP, UDP. Calculates and sets the payload length. Sets the reserved bits to 0. Sets the security parameters index, SPI, to the agreed upon value for the SA. Sets the sequence number, if anti-replay protection is enabled. Appends the calculated ICV as the authentication data field. The sender inserts the A header between the IP header and the transport layer header, example TCP, UDP. The sender sends the IP packet. 3. Receiver processing *. The receiver receives the IP packet with the A header. The receiver uses the SPI and the destination IP address to look up the corresponding security association, SA, in its security association database, SAD. The receiver validates the A header. If anti-replay protection is enabled, it checks the sequence number. If the sequence number is too low, within the replay window, the packet is discarded as a potential replay attack. The receiver recalculates the ICV using the same cryptographic hash function and shared secret key as the sender, over the same portion of the packet, excluding mutable IP header fields. The receiver compares the calculated ICV with the ICV received in the authentication data field of the A header. If the calculated ICV matches the received ICV, the packet is considered authentic and has not been tampered with. The receiver removes the A header and forwards the packet to the next layer protocol, example TCP, UDP. If the ICVs do not match, the packet is considered invalid and is discarded. An error message may be logged. 4. Mutable IP header fields. A crucial aspect of the A calculation is that certain fields in the IP header are not included in the ICV calculation. These are called mutable fields, and they are allowed to change during transit without invalidating the A. The typical mutable IP header fields are *TTL, time to live. This field is decremented by each router that forwards the packet. *header checksum *, this field is recalculated by each router that modifies the IP header. It's specifically designed to detect errors in the header itself. *flags example fragmentation flags. These fields change during routing and transport. Including them in the ICV calculation would make A unusable because every router hop would invalidate the signature. 5. Security considerations. Key management the security of A depends heavily on the strength and management of the shared secret key. A strong, randomly generated key should be used, and it should be securely exchanged using a key exchange protocol like IKE, Internet Key Exchange. Compromised keys can allow attackers to forge packets or tamper with existing ones. Cryptographic algorithm selection the choice of cryptographic hash function is also important. Weaker algorithms, example MD5, SHA-1, are more vulnerable to collision attacks, where an attacker could create a modified packet that produces the same ICV as the original packet. It's generally recommended to use stronger algorithms like SHA-256 or SHA-384. Replay attacks if anti-replay protection is not enabled, A is vulnerable to replay attacks. An attacker could capture a valid packet and retransmit it later to cause harm. Using sequence numbers provides protection against this attack. No confidentiality it's crucial to remember that A does not encrypt the payload of the packet. If confidentiality is required, ESP must be used. An attacker can still eavesdrop on the packet's contents. Fragmentation ipsec can be used in conjunction with IP fragmentation. There are complexities in handling fragmentation when using A. It is recommended to use path MTU discovery, PMTUD, to avoid fragmentation if possible. If fragmentation is necessary, careful configuration is required to ensure that A can still provide adequate security. 6. Code example, simplified, for illustration only. This example demonstrates a simplified A processing, focusing on the ICV calculation and verification. This is not a production-ready ipsec implementation. It lacks features like key exchange, security association management, anti-replay protection, and proper error handling. It's for educational purposes only. Explanation of the code example *. 1. Setup *. We define sample IP header, payload, and shared secret key. Do not use hard-coded secrets in production. We create the calculate_HMAC_SHA-256 function, which takes the data and key as input and returns the HMAC SHA-256 hash, the ICV. 2. Sender side *. We reconstruct the data used for ICV calculation. This is the most critical part. It must match the portion of the packet that the receiver will use for its ICV calculation. In a real implementation, you'd need to carefully identify and zero out the mutable IP header fields before calculating the ICV. This simplified example just includes the full header and payload for brevity. We calculate the ICV using HMAC SHA-256 with the shared secret key. We construct the A header, setting the next header, SPI, sequence number, and authentication data fields. We create the complete packet by inserting the A header between the IP header and the payload. 3. Receiver side We extract the IP header, A header, and payload from the received packet. We parse the A header to get the SPI, sequence number, and ICV. We reconstruct the data used for ICV calculation exactly as the sender did. We calculate the ICV using the same algorithm and shared secret key. We compare the calculated ICV with the received ICV. If they match, the packet is considered authentic. Otherwise, it's considered corrupted or spoofed. Important considerations for the code example asterisk. Mutable fields the code doesn't correctly handle mutable IP header fields. A real implementation would need to zero out the TTL and header checksum, and other mutable fields, before calculating the ICV. Key exchange the code doesn't implement a key exchange protocol. In a real-world scenario, the shared secret key would be established securely using a protocol like IC. Error handling the code lacks proper error handling. Simplified the example is simplified for clarity. A real ipsec implementation is significantly more complex and involves handling various corner cases, security policies, and interactions with the operating system. Security do not use this code in a production environment without thorough security review and hardening. 7. Advantages and disadvantages of A. Advantages strong authentication provides strong authentication of the sender. Data integrity guarantees data integrity, detects tampering. Simple implementation A is generally simpler to implement than ESP because it doesn't involve encryption. Suitable for cases where confidentiality is not required. Useful in scenarios where confidentiality is not a primary concern, but authentication and integrity are critical. Disadvantages No confidentiality does not provide encryption, so the payload is transmitted in clear text. Less flexible than ESP A only provides authentication and integrity, while ESP provides both confidentiality and authentication. Mutable field handling the need to carefully handle mutable IP header fields adds complexity to the implementation. NAT traversal issues A can have issues traversing NAT, network address translation, devices because NAT often modifies IP header fields, which would invalidate the A signature. ESP is generally preferred in environments with NAT. 8. When to use A versus ESP. Use A when authentication and data integrity are the primary security requirements. Confidentiality is not required or is handled by another layer of security. You need a simpler implementation than ESP. NAT traversal is not a major concern. Use ESP when confidentiality is a requirement. Authentication and integrity are also needed. NAT traversal is a concern. ESP is generally better at traversing NAT. More flexibility and security features are desired. In practice, ESP is more commonly used than A because it provides both confidentiality and authentication. 9. Conclusion. The authentication header, A, provides a mechanism for strong authentication and data integrity in IPsec. While it does not offer confidentiality, it can be a useful option in specific scenarios where authentication and integrity are the primary security requirements. Understanding the A header format, how it works, its security considerations, and its advantages and disadvantages is crucial for designing and implementing secure IPsec-based network solutions. Remember that a robust key exchange protocol, like IC, and careful implementation are essential to ensure the security of A. Always prefer ESP when confidentiality is a concern.